Well, good morning, children. We all have studied the nature of electric charges. The like charges repel each other, unlike charges attract each other. Right? Now the question arises, how much will be the attractive force if it is a pair of unlike charges? How much will be the repulsive force if it is a pair of like charges? So, how to account for this force? How to calculate the force? So, the calculation of force and measurement of force is done by referring to a very important law called as Coulomb's law. Coulomb's law of electrostatic force. Right? It is just similar to the gravitational law, that is law of gravitation, universal law of gravitation, which we have learned last year. Universal law of gravitation. Recall that universal law of gravitation. If there are two masses, m1 and m2, separated by some distance r, if their centers are separated by a distance r, then we have learned universal law of gravitation, Newton's universal law of gravitation, which states that the force of gravitation existing between them, force is directly proportional to product of mass, the product of the masses. And this force of gravitation, force of attraction, is inversely proportional to square of the distance separating those two centers. Right? So when we combine this, we got the expression G m1 m2 by r square, where we call this as the force of attraction existing between two any masses separated by a distance r, where their centers are separated by a distance r. And this G is, as you know, is universal gravitation constant. This is Newton's law of gravitation, and G is universal gravitation constant, which does not depend on any medium separating those two masses. This is what we have learned. On the same line, we are going to learn a very important law which governs the electrostatic interaction between two charges. Let us say there are two charges, say plus q1 and plus q2, separated by some distance, let us say r. Then we know that these two charges being like charges, there will be force of repulsion existing between them. Then how to measure this force of repulsion? So according to statement of Coulomb's law, the force of interaction, whether it is repulsion or attraction in the case of pair of unlike charges. In case of pair of unlike charges, it will be force of attraction. In this case of pair of like charges, it is force of repulsion. This force of repulsion is directly proportional to the product of charges. Just like force of attraction, gravitational force of attraction between two masses. These are the masses. M1 and M2 are the masses. It is directly proportional to product of masses and inversely proportional to square of the distance separating those two centers. Here it is directly proportional to product of the charges. Given Q2 are the charges, and this force is inversely proportional to square of the distance. And thus, joining these two factors together, we can write these two equations imply that force of interaction is directly proportional to the product of charges and inversely proportional to square of the distance separating those two charges. Now, these are the charges, or you can say when we take them as point charges, or you can say it is a charge bodies, considering them as point charges, right? Q1, Q2 are the point charges, just like M1, M2 are the masses which we termed as point masses. Here these are point charges. Q1, Q2 are point charges. It means we are neglecting the dimensions of those time charged bodies, right? So F is inversely proportional to square of the distance and directly proportional to the product of charges. But when you take out this proportionality sign, we get a constant. This constant is dependent on the medium which separate these two charges. Constant K into Q1 Q2 by R square, where K is proportionality constant which depends on the value of K depends on the medium between which these two charges are being kept. Medium of separation of these two charges. Medium may be air, it may be oil medium, may be solid medium like glass, or it may be plastic medium, it may be water medium, it may be any medium, it may be nothing else. Nothing else means free space. The medium which separating these two charges may be free space. Free space means vacuum. So that is what we call as medium separating those two charges, which depends on the medium separating those two charges. So K is not universal, unlike G. G is universal constant, which holds true for any two masses in the entire universe. Whereas this also holds true between two charges, provided the constant, the electrostatic constant here, K, which we are calling it as the constant, which depends on the medium of separation of those two charges. It depends on the medium. When no medium is present, then it is called free space. So let us first study what is the value of this constant for free space. Okay. So first we will write this Coulomb's law statement, and then we will look into this equation, which just appears like the force of gravitation. Here the force of gravitation is always attractive in nature, whereas the force of electrostatic interaction may be attractive if the charges are unlike. It will be repulsive when the charges are like charges. So the force depends on the product of these charges. When the product of these charges is positive, the force is positive, and thus it will be a repulsive force. And the product of charges, if it is negative, then the force will be negative. The negative force shows that it is attractive in nature. So that is what we are going to conclude. So first we will write the statement, that is Coulomb's law statement. Now this is the statement. The force of interaction between any two point charges Q1 and Q2 is directly proportional to the product of their charges and inversely proportional to the square of distance separating those two point charges. So point charges means the dimension of the charge body is neglected compared to the charge. So we consider the entire body consisting of the entire charge as point charge, right? So when two point charges are separated by distance r, then the force of repulsion, here in this case it is force of repulsion. This force of repulsion is directly proportional to product of their charges and inversely proportional to square of the distance separating those two charges. And thus, when you write this, we get F is equal to KQ1 Q2 on R square. So this is just the magnitude of force. We have not yet written the direction of force. The direction of force depends on the product of the charges, right? Now, what is the value of K for free space? Let us say. Here K is equal to 1 upon 4 pi epsilon naught is the value for free space, where free space is nothing but vacuum, where nothing is present, no interacting other particles are present. Such a medium is called as vacuum. So this K value differs from medium to medium. Now this here in this case we have written epsilon naught. So it is pronounced as epsilon, E-P-S-I-L-O-N. Epsilon naught is the constant for the free space. It is called dielectric constant, dielectric constant for free space. So its value is 8.854 into 10 raised to minus 12. 10 raised to minus 12. So you can write the units here. Q1 Q2 upon, yes, Q1 Q2, that is Coulomb square. Coulomb square per Newton per meter square. Coulomb square per Newton per meter square. So if you take this epsilon naught to the right hand side, so we get force in the denominator. So Coulomb square per Newton per meter square. So that is the epsilon naught value, right? So this is called permittivity of free space. This is called permittivity of free space. So we will define what is the permittivity of a free space later on. It means how much that medium allows the interaction of force, how much it is allowing the electrostatic interaction. That is what is written in terms of the name permittivity of free space. So when you substitute this 8.854 into 10 raised to minus 12 in this denominator, then we get K equal to 9 into 10 raised to 9 Newton meter square per Coulomb square. This is the constant, that is electrostatic constant for free space. Right? Now we will discuss the same equation in the vector form. Now let us consider two charges. Now we are going to discuss Coulomb's law in vector form. Coulomb's law in vector form. So for that, let us consider these two charges, Q1 and Q2, okay, and consider the system of coordinates. This is x-axis and this is y-axis. Okay, this is origin, and we draw the position vector. The vector drawn from the origin to the position of a particle is called as position vector. Let R1 vector be the position vector of the charge Q1. In the same way, let R2 be the vector which is the position vector of charge Q2. Now we will find the displacement vector, the length vector, the length of separation of these two distances, of these two charges. We can find out using this vector diagram. So R1 and R2, these are the vectors. Using triangular law of vector addition, this naturally becomes R2 minus R1 vector, that is directed from Q1 to Q2. You can look at the Arrowhead is from Q1 to Q2. This vector is R2 minus R1, and you see this is head. You can verify if you add this, the vector from origin to Q1, that is R1, vector from Q1 to Q2, R2 minus R1. If you add them, so R1 cancels. So according to triangular law of vector addition, R1 plus this vector should be giving you the third vector, that is the third side of the triangle, starting from the tail to the head. The vector originating from the tail to the head. So that becomes the resultant vector. So R1 plus R2 minus R1, R1 cancels, you are left with R2 vector. So this vector which is directed from Q1 to Q2 is R2 minus R1 vector, which is denoted as R21 vector. So this should be specifically understood. So here I am getting R2 vector minus R1 vector is equal to R21 vector. R21 vector. And you look at the direction of R21 vector, it is directed away from charge Q2. Along the line joining the two charges, but away from the charges. This gives you direction of R21. Similarly, if you want to find out the direction which is from Q2 to Q1, then it will be, on the other hand, R12 vector. So we can write here, this is direction along Q2. Right? Similarly, R1 minus R2 vector, if you do this, R1 minus R2 vector, look at this. This is R1 vector minus R2 vector, then it will be a vector in this direction. So this becomes R1 minus R2 vector. So this R1 minus R2 vector is written as R12 vector. It is directed towards Q1, directed towards Q1 from Q2. Right? Now we will write force on 2 due to 1. That is electrostatic force of repulsion that we already know. So I will write force on Q2, force on Q2 due to charge Q1, due to charge Q1. This is written as F21, force on 2, how to read it? Remember, force on 2 due to 1, F21 is equal to, right? According to the equation which we have considered, 1 upon 4 pi epsilon naught. Since we are considering the charges to be in vacuum, these are the point charges. What are the point charges? Q1 and Q2 in vacuum. In vacuum. Then F21, force on 2 due to 1, force on Q2 due to Q1. Definitely we know that it is going to be repulsive force and it is going to be away from the line joining the two charges. Along this F21, I can also write this as the direction of F21, force on 2 due to 1, repulsive force. Then it becomes Q1 Q2 by R21. You can look at this. Direction is R21 vector. R2 minus R1 or R21. I can write one step here. R2 vector minus R1 vector, square of this into, I have to show the direction because this doesn't give us direction. Direction should be the unit vector. The unit vector which is along Q2. The unit vector along Q2 is nothing but R21 vector. Look at this. You can look at this. R21 vector is along the direction of R21. So this I am going to write as R21 vector, R21 cap, where R21 is unit vector along Q2, directed along Q2, away from Q2. Right. Similarly, okay, one more step I can write here. To make look it simple, I can write it as 1 upon 4 pi epsilon Q1 Q2 upon R21 square, R21 cap. So this I am writing as F21 vector. This is the vector form of Coulomb's force. This is also called as Coulomb's force. So this has magnitude also. Magnitude is 1 upon 4 pi epsilon Q1 Q2 upon R21 square, where we already know what is 1 upon 4 pi epsilon. 1 upon 4 pi epsilon is, right, 9 into 10 raised to 9 Newton meter square per Coulomb square. Right. Now, in the same way, I will write now force on Q1, force on Q1 due to Q2. This is also equals. So on the same line I write force on Q1 F12 vector equal to force on Q1 F12 vector equal to, okay, write here 1 upon 4 pi epsilon Q1 Q2 by R12 square, as I have written here directly. R21 is the order here. Now here it becomes R12 square into direction. Look at the direction. Direction is now towards Q1. It is in this direction towards Q1. So R12 cap, where you can write R12 cap is unit vector directed towards Q1 along line joining the charges along Q1. So you can call this equation as 2 and this equation as 1. So look at the vector diagram. From the vector diagram and previous one, from this analysis, what do you understand? R2 minus R1 vector is along Q2. R21 vector is along Q2. Then R1 vector minus R2 vector is along Q1, directed towards Q1 along from Q2, that is along Q1. So this becomes R12 cap. This is R12 cap, and the direction of force is also along the same line, F12 vector. Now from the diagram and from this, we can see that R12 vector, R12 cap is equal to R21 cap with negative sign, because they are of magnitude 1 but exactly in opposite direction. Therefore, R12 vector is equal to minus of R21 vector. Thus, from equation 1 and equation 2, we write magnitudes are no doubt they are equal. F12 from equation 1 and equation 2, and write F12 is equal to negative of F21, because if you replace this R12 vector with minus R21, what happens? We get F12 vector is equal to 1 upon 4 pi epsilon Q1 Q2 by R12 square. R12 vector is nothing but minus R21 vector. Minus R21 vector. Right? When you substitute this minus R21 vector, take this minus R21 here. So if you take this minus sign, then this entire equation, is it not number 1, that is F12, becomes minus of F21. Thus, force on 1 due to second charge is equal and opposite to force on 2 due to first charge. Thus, this is also in accordance with Newton's third law. For every action in an interaction, the interaction here is electrostatic interaction. In an interaction, for every action, there is an equal and opposite reaction. For a force exerted on 2 due to 1, the force exerted on 2 due to 1 is equal and opposite to force exerted on 1 due to 2. Is it not Newton's third law? This is also realization of Newton's third law. So, the forces of interaction are equal and opposite in direction. So, if the charges are, look at this, the charges are light charges, then the forces are, you can see the forces are force on 2 due to 1 is force on 2 due to 1 is away from the point charge. Force on 1 due to 2 is also away from the point charge. So the forces are acting along the line joining their centers, but they are away from each other. This is representation of repulsive force. Repulsive force. Force is repulsive if and only if it is positive. If and only if the force is positive, because in that case the product Q1 and Q2, the product is positive, because Q1 Q2 product is positive. On the same line, if you look at it, suppose it is a pair of positive and negative charges, Q1 and this is Q2. This is the line joining the two charges. Then you will get force of attraction directed towards Q1. This is F21 directed towards Q1, and force of attraction again towards Q2. This is F12. So this is how we represent force of attraction, and force of attraction will be negative. How it will be negative? This will be negative. Why it is negative? You can just see. Before that, you can write this force is attractive in nature. Attractive in nature because the force is negative. The force is negative here because reason is the product Q1 Q2. Look at this is negative. The product Q1 Q2 is negative. Thus, we have written the Coulomb's law. Coulomb's law in vector form. Coulomb's law in vector form is written by force with a vector which has both magnitude as well as direction. So, repulsive force is denoted by the forces which are acting away from the charges. Attractive forces are represented by the forces which are acting towards each other, mutually attractive forces. Attractive forces, it is negative force. Force is negative. Reason is the product of charges is negative. Force is repulsive if and only if the product is positive. The product is positive if and only if the charges are like charges. When Q1 and Q2 are like charges, product is positive. When the product is positive, force is positive. When the force is positive, that is nothing but repulsive force. If in case the charges are unlike, then the product Q1 Q2 is negative. Q1 Q2 product is negative. When the product Q1 Q2 is negative, ultimately the force is also negative. The force negative implies it is attractive interaction. It is attractive force. Remember, whenever the force is negative, it implies attractive force. Whenever the force is positive, it implies repulsive force. Gravitational force is always attractive in nature, therefore it is always negative force. Okay, we'll discuss more about it in the next session. Okay, thank you, have a nice day.